We have two very different functions, so we're going to begin by analyzing them separately. Our first one here, y equals ax squared. Since a is positive, this is an upward opening parabola at the origin. Let's take a look at this second graph with our floor function. I like to analyze this using a table of values. Let's start with x equals 0. The floor is 0, the fractional part is 0, so y is 0. A little bit to the right, we can try x equals 0.2. Floor is 0, the fractional part is 0, and y is equal to 0. We can see that between 0 and 1, we're always going to have the floor is equal to 0, so our y-coordinate is going to be equal to 0. At x equals 1, the floor is 1, but now the fractional part is 0, so we still have y is equal to 0. Moving a little bit to the right, at 1.2, the floor is 1, the fractional part is 0.2. At 1.8, for example, the y-coordinate is 0.8. So it seems like on this interval between 1 and 2, we have a segment with a slope of 1. At x equals 2, our floor is 2, the fractional part is 0 again, so we start over again at y equals 0. Moving a little bit to the right, here at 2.2, y is equal to 0.4. At 2.8, y is equal to 1.6. So we see on this interval, because the floor is always equal to 2, we're going to have a line segment with a slope of 2 going from y equals 0 up to y equals 2. And we start over again at 3, where y again is equal to 3, and we're going to have a slope of 3. Let's take a look at what happens when x is negative. For example, at negative 1.2, the floor is negative 2. The fractional part is 0.8. We get a y that's negative. And since our parabola has a is greater than 0, it's an upward opening parabola. So we're not going to have any intersecting points when x is negative, and we can ignore those. Let's graph this function. On the interval between 0 and 1, our y-coordinate is 1, so it looks like this. On the interval between 1 and 2, our y-coordinate goes from 0 to 1. So we have a straight line segment with a slope of 1. On the interval from 2 to 3, we have a straight line segment from 0 to 2 with a slope of 2. On the interval between 3 and 4, we have a straight line segment that goes from 0 to y equals 3, and this has a slope of 3. We have a disjointed function, so we can define it piecewise. On the interval between 0 and 1, the equation for this segment is y equals 0. We can imagine our parabola with a vertex at the origin going off in this direction. And these points of intersection are going to be the points that satisfy our equation. And we're looking to sum the x-coordinates of all these solutions. And we want that sum to be equal to 420. Examining this in a piecewise fashion, on the interval between 0 and 1, the equation of the orange segment is y equals 0. We set that equal to the equation for the parabola. Since a is positive, we have x is equal to 0, but this isn't contributing to our sum, so we can disregard this. When x is in the interval between 1 and 2, the equation for our orange segment is y equals x minus 1. Set this equal to the equation for our parabola, collect all the terms on one side, and solve using the quadratic equation. We'll continue with x in the interval between 2 and 3. The equation for this line segment is y equals 2x minus 4. Set it equal to the parabola and solve for x. I'm going to factor out the 2 because when I do that, I get the solution for x in the previous interval. Let's consider x in the interval between 3 and 4. The equation for this line is 3x minus 9. Solving for x, we get 3 times what the solution was in the interval between 1 and 2. So we can generalize. When x is in the interval between consecutive integers m and m plus 1, the equation for our line is mx minus m squared. Solving for x, we get m times the expression for x in the interval between 1 and 2. The problem here is from the quadratic formula, we actually have 2 solutions on each interval, but we're expecting only one solution. But we see that the equation for this segment, if we extend it into a line, we're going to have a second solution up here. So it's clear that we're always interested in the smaller solution. This is where x is equal to m times 1 minus root 1 minus 4a over 2a. We are given that the sum of all of these solutions is 420. So as m goes from 1 to some endpoint k, We want the sum of all of these solutions to be equal to 420. We can factor this expression out, and this sum is just the sum of consecutive integers from 1 to k. So we can use our formula for the sum of consecutive integers. And what I'm going to do is I'm going to pull this k out in front of this expression and then divide the left-hand side by k plus 1 over 2 and the right-hand side. So we have this expression. On the left-hand side, this can be thought of as the solution for x on the interval between k and k plus 1. If x is in this interval, then this expression is also in this interval. And so we have 840 over k plus 1 is also in this interval. So let's write this as a chain inequality and multiply through by k plus 1. Now we're going to experiment and find values of k that are in this neighborhood. When k equals 29, our lower bound is too high. So we try k equals 28, which works as our lower bound, and it works for our upper bound. What this means is we want our last intersecting point to occur in this interval between 28 and 29. So our parabola is going to come in through here like that. But this leads us to wonder whether our parabola might not have two intersecting points on this interval. So it might look something like this. So which one is it? We want to check to see that there aren't two solutions on this interval between 28 and 29. If there are two solutions, we can see that this distance is going to be less than 1. So let's check and see what's happening with our two solutions on this interval. At k equals 28, our solutions for x are 28 times 1 plus or minus the square root over 2a. This represents two solutions, and we're going to find their difference. When we subtract, we get this expression. What we want to know is this less than 1? In order for there to be real solutions, the discriminant tells us that a must be less than 1/4. So let's try a smaller number, a equals 1/5. Let's get that a in the denominator under the square root sign. Substituting a equals 1/5, we get 28 times the square root of 5, and this is much larger than 1. So we're not going to have two solutions on this interval. So let's figure out what a is equal to now that we know that k is equal to 28. Substituting, divide by 28, isolate a, square both sides, gather all the a terms on one side, factor, and then solve for a. We get a is equal to 29 over 900. So that gives us p plus q is equal to 929, or answer C.